So let's demonstrate that. Let's consider a situation where we have a 25 kilogram box sitting on a table, and we're going to pull on it with a rope. And that rope will be at an angle theta, and we will consider the situation where that angle theta is 0 degrees, 20 degrees, and 60 degrees, and we will pull with a tension of 105 newtons. Okay, so the first step is to draw a free body diagram. In the simplest case, where I pull it directly horizontally, all of my forces are a gravitational force, mg down, a normal force, n up, a tension force to the right, and a frictional force to the left. We can write an equation, Newton's second law equation, in the y direction, and that will simply say that the normal force minus mg is equal to may, but of course ay is 0, so that simply states that the normal force is equal to mg. So in this case the normal force does equal the weight. Then the comparison is to find out what the maximum frictional force is and compare that with the tension. Oh, I forgot to state that we'll assume the coefficient of static friction is 0.45. So, the maximum friction is μs times n, which will be μs mg, or in other words, 0.45 times 25 kilograms times 9.8 meters per second squared. Let's pull out a calculator. And I have 0.45 times 9.8 times 25. Aha! That's a force of 110 newtons. So, the maximum static friction is 110 newtons, whereas the force I'm pulling with is only 105 newtons. In other words, I am not pulling with enough force to overcome friction. So in this case, it is not going to move, and I can do a Newton's second law equation in the one dimension, so in the x direction, I now have tension minus friction equals max, which I now know is 0 because I don't have enough to move it, and that just tells me that the tension equals the friction, which is 105 newtons. And I'm done. So when I pull horizontally, it doesn't move, and the friction is just equal to the tension, 105 newtons. Now let's consider the case at an angle, and we'll try it out both at a 20-degree angle and at a 60-degree angle. So, same box, same tension pulling upward at an angle theta. But in this case, the free body diagram's a little more complicated. The tension being at an angle has to be broken into a horizontal component and a vertical component. And then I'm going to put two little lines through here to remind me that it's no longer that force there. I'm using the two components. This one is t times the sine of theta. This one is t times the cosine of theta. And I still have a normal force. I still have gravity. And I still have a frictional force. But now when I look in the y direction, things are a little more complicated. I still have a normal force pulling up, I still have mg pulling down, but I now also have t sine theta pulling up. That all is equal to m-a-y, but again a-y is 0. So in this case the normal force is only mg minus t sine theta. Let's actually figure that out in this particular case. So that is 25 kilograms times 9.8 meters per second squared minus 105 newtons times the sine of 20 degrees. Let's pull out the calculator. 25 times 9.8 is 245. Minus 105 times the sine of 20 degrees. That's 35.9. And that leaves me with 209.1 newtons. Really, I only have the one significant figure, or the significant figure to the ones point, so it's really just 209 newtons. So my normal force is less this time. It's only 209 newtons. Well then, let's see what that tells me about my frictional force. My frictional force, then, is μs times the normal force, or in other words, 0.45 times 209 newtons. I know I've got a negative sign sitting there. I'll put that there to get rid of it. Oh, this time the frictional force is only 94 newtons, less than my tension. However, I can't just immediately say that that means I will be able to move it, because of course now I don't have the full tension pulling horizontally. I have only t cosine theta pulling horizontally. Let's see whether or not that's enough to move it. So in this case, t cosine theta is equal to 105 newtons times the cosine of 20 degrees Oh, look, that is 98.6 or 99 newtons. And look, in this case, I do in fact have more force pulling than frictional force, so it will slide. Of course, then we have to ask the question of how fast will it accelerate? That's an excellent question. To do that, though, I need to figure out what the coefficient of kinetic friction is. Let's assume that the coefficient of kinetic friction is 0.30. Notice it's significantly less than the coefficient of static friction, and that's normal. In this case, the frictional force will be mu k times n, which is simply 0.30 times the normal force of 209 newtons, or 62.7, or essentially just 63 newtons. To find the acceleration, I know that the sum of the forces is equal to ma. The sum of the forces is the 99 newtons to the right from the tension, from the horizontal component of the tension, minus the 63 newtons to the left from the kinetic friction. That's going to leave me with 36 newtons. And the acceleration is then the net force divided by the mass, 36 newtons divided by 25 kilograms. A newton is a kilogram meter per second squared. Notice kilograms cancel, leaving me with meters per second squared, appropriate acceleration units. And this is going to be about 1.5. But let's pull out the calculator. And we have 36 divided by 25 is 1.4 meters per second squared. I've essentially lost some significant figures in the subtracting here, so I think that's about the right number. Alright, so the last case we want to consider is the case of an angle of 60 degrees. We saw that an angle of 0 degrees it would not move, an angle of 20 degrees it would move. What happens at an angle of 60 degrees? Well, let's take a look. I want to keep some of this stuff, so no, that's not what I wanted to do. The reason I'm keeping this is much of that is the same. So when I come to a new page, I paste it. Okay. This formula for the normal force is still correct. The numbers are not, but it's similar. So I still have 245 newtons minus 105 newtons times the sine of 60 degrees now. So it's going to be a significantly smaller normal force. So 105 times 60 sine. Oh, I'm going blind. That is my equal sign. Okay, so that's 90 negative, and add that to the 245. So in this case, my normal force is only 154 newtons. That's my normal force. Which means we can use this same formula over here for the maximum frictional force. F static max is 0.45 5 times 154 newtons. Look at that. In this case, we have a frictional force of only 69.3 newtons. Now, we also have to check the tension force that we have. So the tension force we have in this case, T cosine theta, is equal to 105 newtons times the cosine of 60 degrees. Well, look at that. Even though we have such a small frictional force now, in this case, we only have a tension force, a horizontal tension force of 52.5 newtons, which, if you notice, is less than the maximum frictional force, which means the maximum frictional force will just be enough to match it. In other words, T cosine theta minus F will equal MAX, which is 0. So the frictional force will simply equal T cosine theta, which is just 52.5 newtons. So notice we found that at the lowest possible angle, the normal force was simply the weight. And in this situation, we did not have enough force to overcome the friction. At a small angle, we were able to lower the normal force enough to lower the friction that we were able to move it, and we had a significant acceleration. However, when we went to a high angle, we lost so much force pulling sideways that we were no longer able to budge the block. A very interesting problem. I will do a supplemental video where I show how to look at this problem, really how I came up with the equations or the values for the problem, and how to find what is the optimal angle to pull the block. But I don't want to put that here in the middle of this lecture.